This is group five. We're going to be presenting the data we gathered based on the published article for electrochemical thermal analysis of lithium ion batteries. So we are in the process of trying to replicate 8 models that have been presented in the published article, which contained a combination of thermal and electrochemical models. And in the next slide, I have started with the first model, and so far, I've gathered the temperature and voltage profiles after a period of time. And as we can see, based off the temperature profiles, there is uh, a greater temperature reached for greater discharge rates. And for the voltage, we have a faster drop in voltage with greater discharge rates. And this is completely different from the presentation that we have submitted last time, as I gained errors because I had a linear model. In the next slide, I have presented the second model. And once again, they are temperature and voltage profiles, which do seem similar, especially the voltage profiles as the first model. But in the temperature profiles, there's a distinct difference between the higher discharge rates of 2C and 1C. On the previous model, we have reached below 35 degrees Celsius, and right here, 2C has reached above around 36 degrees Celsius. Next.
So these are the models for the homogeneous models 3 and 4 for the research. Um, Currently, I'm having issues modeling the electrochemical aspects in MATLAB to reflect accurate voltage changes. The voltage values that I currently have remain unchanged until a sudden drop, as you can see in the figure. There's issues with that I need to resolve. But results for my zero point 0.5 to my 2 Coulomb models are similar to what is expected. Next slide, please. For temperature versus time, my results are higher than expected, as well as I have a faster temperature increase rate. Those That's also, I believe, is due to my electrochemical model being off currently. Next slide, please. Here is the heat generation for Model 3. This includes the ohmic, reversible, and polarization heat. My 2 Coulomb model shows a significant increase in ohmic resistance or ohmic heat generated, a lot higher than what would be expected, being at 0.6 watts. Next slide, please. And then these are the results for my heat generated for Model 4. Next slide. Going forward, I need to plot my temperature versus DOD percentage with varying transfer coefficients for models 3 and 4. Like I said, I need to fix my issues with my zero point 0.2 Coulomb modeling. Something's off with it, and I need to plot my state of charge changes versus DOD percentage to see what's wrong with my current electrochemical model. Next slide.
I'm Jacob Roberts, and I've been covering Model 5 and Model 6 in this research. So to start off, I updated my temperature versus time plots for Model 5 and Model 6 because when I originally created them, they were all the temperatures for each discharge rate were kind of trending in a negative direction from the starting temperature of 25 degrees Celsius. So this is my updated version of temperature versus time for Model 5. And the next slide is the updated version for Model 6 as well. Next slide. And then I had started working on the heat generation rate versus the depth of discharge of the batteries for both Model 5 and Model 6. I had I had made separate plots as a way to compare both Model 5 and Model 6 for each discharge rate that they both share. So this first one is at the discharge rate of 0.5 C. And you can kind of see that the plots are very quite similar to each other between Model 5 and Model 6. And the next slide would just be kind of the same plot for just at a different discharge rate of 1C. And then next slide would be at 2C for both Model 5 and Model 6. And the next slide, I generated just a total heat generation for versus time instead of the depth of discharge for both models. And this is kind of sort of the trend lines I got for Model 5. And then the next slide would be for Model 6. And the overlays include the different discharge rates for each model.
Alright, so hi, I'm Isaac Sorrells and I worked on Model 7 and 8 for lithium-ion battery. For Model 7, I used a 2-node core shell thermal setup, and as we increase the C rate, the core always stays a few degrees hotter than the surface. At 2C, the core reaches around 45 degrees Celsius, while the shell is about 42 degrees Celsius. The voltage curve also shows a larger drop this week based on a modified equations in MATLAB. In Model 8, I used a simpler lumped model, but varied the convection coefficient from 22.5 to 67.5 watts per square meter Kelvin. And we see that the higher H values greatly reduce the temperature rise from about 20 degrees down to 8, which matches pretty well with the paper's trend. And then the main result that I worked on for this week was the heat generation, and I worked on the heat generation for Model 8. I prepared a ohmic, polarization, and reversible terms, and then a total term for all of them. And we see that the ohmic heat dominates early, polarization increases towards the end, and reversible heat is small but changes sign with entropy.